Diese Konferenz wird nun aufgezeichnet.
Hello and welcome to everyone to this presentation with the very bulky title, Thermochemical Equilibrium Modeling of Ash Transformation during the thermal conversion of different biomass types with a focus on the speciation of phosphorus and potassium. I would say I will start right away since our time is limited, and I just want to give you a quick overview about the content I want to talk about today. It's the practical setup, basically our experiments in practice that we try to model, the databases we're applying for the modeling, the input parameters and how we're varying them, and how we're extracting the data and evaluating those after we basically created them. And as it is outlined in the content, I will start with the reactor system that we use in practice. At the moment, we're using a macro TGA, which is set up in our laboratory. It has a continuous gas inlet of 7 liters per minute with a specified gas mixture of nitrogen, CO2, O2, and water. Basically, the water is inserted as liquid water, but it evaporized, and therefore we can assume it's in the gas phase in the reactor. The temperatures we're analyzing are in the range of 600 to 950 degrees Celsius, which is the upper limit of the temperature, the 950. The residence time of the particle that you can see in here, which is the fuel sample, is between 10 and 240 minutes. And we have a quenching zone in the upper area here where we can purge with nitrogen to make sure that we don't have any additional reactions. And the sample size is 700 milligrams. So this is what we want to model with the approach. The fuels we're using are basically biomass fuels. Here you can see a variety of different biomass fuels which originate like purely from nature. And you can see that there is a huge variation in the elements that are in the system, like basically the primary element changes. It can be calcium, silicon, it can be potassium, and also phosphorus. And also the specific amounts of those elements in the ash are highly varying. As you can see, for example, for the phosphorus, we have one fuel, which is the wheat grain residue that has a very high phosphorus content. The other is not so high. In grass, it is at least noticeable. The other type of fuels we're analyzing are sewage sludge and sewage sludge mixtures with agricultural residues. As you can see in here, sewage sludge is very rich in ash. That's the basic asset of sewage sludge. It has like 33 weight% dry fuel ash content. So whatever elements you have in there, there will be a lot of them if you prepare any kind of mixtures with it. And as you can see, it is also very heterogeneous in comparison to other agricultural residues. It has a lot of silicon, phosphorus, iron, calcium, and aluminum, which basically creates a very large element pool ready to react in any kind of modeling or also in reality. And these are the types of fuels that we analyze in practice. So therefore, they're also the fuels that we analyze in our modeling. And the mixtures that we prepared in practice and in the modeling are based on the phosphorus to potassium ratio, because we want to alter the speciation of phosphorus. And this is like going into the research motivation that we have. We want to close the anthropogenic phosphorus cycle, which means that we just want to recycle phosphorus that is leading the anthropogenic cycle, because otherwise we would have to create it again from phosphate rock, for example. And we want to do this by making use of potential potassium-rich residues to create, and that's the next part probably, to create more bioavailable phosphates. So the research gap that we currently are aware of is that we need to alter the phosphate speciation to actually create bioavailable phosphates. And our research gap also includes that we don't know the influence of the process parameters, for example, the gas atmosphere. How does this go into the thermochemical calculations? Well, in those calculations, we try to analyze what kind of phases we expect in the condensed ash phases at the process temperatures. For example, what kind of melt do we have? What kind of stoichiometric compounds? Furthermore, we also want to see how much melt is actually formed, because that's a very important process parameter. And we need to know that to get, for example, into larger scales, because melt formation can cause huge problems in the operation of such systems. Furthermore, we want to see what kind of phases would precipitate from the molten ash. And also we want to see which elements could be released from the system. So especially potassium, which we already know is very readily volatilized in thermal conversion systems. We want to see if those release rates can be determined with the calculations as well. And in the end, we want to analyze if our equilibrium state in reality is getting close to the one we model, or if we are far away from that one, and if that equilibrium state actually favors what we want to achieve, basically the alteration of phosphates. The databases and input parameters that we're using are based on the fuel parameters as well, because we need to choose a database that is suitable for the specific fuel composition. This basically means that we have to use a system that can include carbonate melts if the system is expected to create such carbonate melts, especially when we have cation-rich fuels. On the other hand, we also use SGPS and detox as a combination because of the complexity of the phosphate compounds that we want to determine in our system, because we have in most of our fuels that we're analyzing a lot of phosphorus. Furthermore, we want to model a gas input without setting activities, because that gives more constraints to the system. We have ash element manipulation, which basically reflects our mixtures. We analyze in the temperature range from 600 to 1200 degrees Celsius, and we simulate the gas atmosphere by simulating the lambda value for the gas conditions and the gas proportion. And now I actually want to get directly into the results of our analysis. We have two different types of fuels. Basically, we determine that they are these type of fuels. We have the cation dominated fuels. They can be forming, for example, magnesium and calcium carbonates. And those carbonates are highly stable, or they actually do not volatilize, but rather form, for example, the oxide. So they volatilize just at higher temperatures. But also we have carbonates, for example, formed by potassium, which are not really favored if they're in competition with other compounds, but they volatilize at lower temperatures, which we can detect in reality and in the modeling approach. And for these kind of fuels, we actually need to include a database that tells us something about salt melts that can be formed as well. On the other hand, we have anion-dominated fuels, which create a more complex system and a very complex solid solution system as well. They can be found more or less in this corner. This is the triangles I put in here are more or less like approximations of the areas. And you can see that a lot of fuels we have in here are actually in the anion-dominated fuel region. And here we have a system where oxide melts are mainly formed, and they are triggered by the availability of silicon and phosphorus. And additionally, the gasification may influence the oxidization state of the compounds in there, which is very important because for an element that's not listed in here, iron, this can actually change the system, as we can see later. Now to the results from actual calculations, for example, the initial melt formation. These is done for the sewage sludge mixtures. As we can see in this graph, we have to the very left a deviation between the systems when it comes to gasification and combustion. This is due to the detection of a different oxidization state of iron in our system. Basically, we can create iron phosphates because we have an excess of phosphorus on a molar base in our ash composition. So we have the availability, or more or less, we have the potential to create iron phosphates. And due to the gasification, we change the iron state more or less, which then creates lower melting compounds in there. So we detect a very low initial melt formation for the mixtures that are very high in sewage sludge. On the other hand, when we go to this side, we have a diverging trend when we add agriculture residues based on which type we add. We have sunflower husks, which is very low content, which has a very low content in silicon, and we have wheat straw, which has both potassium and silicon in there. And those are diverging a lot because we have the formation of a potassium silicate melt in wheat straw, but not in the sunflower husks, which assumes a very high stability. On the other hand, we need to question our approach in here because we all modeled this with GTOX SGPS, which gives us the information that it might not be applicable for this region because we're in a cation dominated region. On the other hand, in comparison to the sewage sludge, we can see little impact of the gasification. For the melt development, it shows a similar picture, but we can see that the sewage sludge, though melting at low temperatures, shows a very flat gradient in comparison to the wheat straw, which shows a very high gradient, more or less, and it shows initial complete melting in a very short temperature range. And by addition of sewage sludge, it actually improves. It is the other way for sunflower husks, where we can see that we have very high melting temperatures, although we need to question those. But it gets slower because of the addition of sewage sludge, most probably because we have more silicon and phosphorus availability. In this slide, I don't want to highlight the results as much because, first of all, they're very small and like they more or less give just information that we need to process afterwards. What we try to do here is we try to group the phosphates by literature, so by the potential plant availability. So we group them into different groups of their association, let's say it like that. And we can see that the potassium phosphates are highly favored, which is good for us because we assume the potassium phosphates are the type of phosphates that we're looking for. Although the calculations also indicate that there is a very strong hierarchy. In terms of temperature dependence, we can see that especially the iron and aluminum phosphate system, like the phosphates that bear also iron, are very readily incorporated in any kind of melt, whereas the calcium magnesium phosphate showed the highest temperature resistance, more or less, like resistance referring to they were in solid state and not incorporated into the melt even at higher temperatures. And other phosphates are more melt affine than the calcium magnesium phosphates. This can be pure calcium phosphate or pure magnesium phosphate as well, of course. Another approach we chose is the melt precipitation. So basically we took the melt that we formed that indicated temperatures and precipitated it. Again, the results in here are just to highlight how we present our results. The main conclusion that we can take from them is that we can probably enrich one fraction of the ash, in this case the melt, with potassium and phosphorus, and therefore favor the precipitation in that case of potassium phosphates. This is somehow important because in the overall ash composition, you always have the competition between different phosphates. But if you can enrich potassium and phosphates in one certain region of the ash, then you could probably produce more of the potassium phosphates. So shift more or less you could not shift the total equilibrium, but the individual equilibrium for melt and solid fractions, for example. So, and what we can see in here as well is that potassium phosphates are preferred over, for example, potassium silicates when it comes to precipitation, because we precipitate a lot of the silicon more or less as pure or as tectosilicates. And now I actually want to come to the conclusion already because our time is limited, as I said. And our conclusion is that the database and element selection is the most crucial step. Like in the beginning, this is what you need to focus on. But our results also indicate that the thermodynamics favor our goal of the phosphorus alteration from calcium phosphates to potassium bearing phosphates. Also, we can see that the melting behavior changes significantly dependent on the mixture. We have increased melting temperatures in wheat straw, like when wheat straw more or less gets an additive of sewage sludge because we inhibit potassium silicate formation. But sunflower husks, since they don't contain like a lot of phosphorus or silicon, it actually shows a decreased melting temperature. Also, we can see that phosphorus and potassium have a high affinity towards the melt, and therefore we need to expect amorphous structures as well in reality. And it was a very suitable guideline for our experimental design. So we could actually design a lot of stuff like more or less derived from our calculations. However, we have a lot of unsolved issues as well. And one of them is the hydroxyapatite formation, which is more or less not represented as a stoichiometric compound. The complexity of the Whitlockite system, which is in reality more complex than in our calculations. This problem with database adaptation and selection in terms of cation anion ratio, systems with continuous gas flow, and especially sulfur when it comes to STPS and GTOX, and also the hierarchy of formation. So because the hierarchy is very strong in our stoichiometric compounds formation. Furthermore, we miss a lot of viscosity parameters. So it's nice to know a lot about the melt, but we also need viscosity parameters to actually know what we're dealing with in reality. And this more or less leads us to the issue that we want to have a uniform methodology in our approaches for our ash chemistry. And this would be very helpful to get this in cooperation with developers, in cooperation with people who have it in practice, to really have the methodology set up and comparability enhanced. And this is how I want to end, and I thank you for your attention, and I'm ready for your questions.